Okay, this will be lecture 6 on tangible incompleteness by Harvey Friedman, please.
Yes, this is lecture 7, actually.
Sorry. Yeah. Indeed.
Yes. Today we start this reversal, which is rather involved, and I'm going to try to make it understandable. I'm going to put the entire reversal on my downloadable manuscripts page, not lecture note page. So you can look at any details that you're interested in that are inspired by the talk. So I will do that in a few days, as well as put a copy of these lecture notes on the lecture note page. Okay. So now I have to get into the mood of a reversal because we've been just talking about proving these statements. And that's kind of a shift of perspective that's substantial. All right, so to review, in lecture 6, we discussed 48 statements in invariant maximality. Let me move this. How do I do this? Just a second. I'm just trying to. Yeah, I don't see how to. I just want a slightly different view of the screen. All right, I'm going to have to do it this way. All right, so in lecture 6, we discussed 48 statements in invariant maximality in 4 groups of 12 each. Each group is based on a single one of 4 invariance notions. The book singles out 2 of these statements in the 48. The first is finite maximality of root lower z plus order invariance lowered, which implies all of the 48 statements by elementary arguments in RCA naught. And the second is order invariant max cliques less than 1 shift, which is implied by each of the 48 statements by elementary arguments in RCA naught. So we have a strongest statement and we have a weakest statement. Now we already proved maximal order invariant root lowered, which is trivially equivalent to finite max root lowered in WKL naught plus con SRP in lecture 5. We've already done that. And now we begin presenting our proof of that order invariant max clique less than 1 shift implies con SRP over our RCA naught. So I will review all the terminology. So this is lecture self-contained. Actually, this is a white lie. We actually start the reversal with a convenient variant of this OI max clique less than 1 shift that follows easily from it. All right, let's review what these say. So OI max clique less than 1 shift. Every order invariant graph on Q0 n to the k has a less than 1 z plus shift invariant maximal clique. So we've shifted to the graph setup, which is slightly more convenient. This is among the demonstrably equivalent formulations. All right, now what we actually reverse is a variant of this. So this first statement is one of the 48 that is implied by every other one. Every other one implies this one. So the variant is that I move it to -1,1. So this is OI max clique -1,1 less than 0 shift 1 QV. Well, let's first talk about less than 0 shift. So this is every ordered invariant graph on Q -1,1 to the K has a less than 0, 0 over N N over N shift invariant maximal clique. We'll go over that definition, but this is the interval shift invariance. This is the interval shift invariance that we did in very early in the lecture series when we were doing the core mathematics stuff with piecewise linear and piecewise linear and semi-algebraic on the reals. Now, the rationals are a case of the reals, so this is a special case of that definition. That's definition that was made in the early part of the lecture series. Okay, we make one more step, which is convenient, which is to make a consequence. That is, set the variables k equals n, and that's called 1 QV, meaning one quantified variable. So this is the statement we're really aiming at here. All right, now let's go over the definitions of this. Now we're gonna want to know that that this is provable from this other statement that I said all of them imply, right? All right, so definition. S is less than 0, 0 n to n over n shift invariant if and only if for every x in Q -1, 0 union these fractions to the k, leaving out the last one, if x prime is the result of replacing these numbers by these shifts, then x is an S if and only if S prime is an S. That's the definition. And this is a special case of the interval shift invariance discussed in chapter 2. Definition 2.3.1. All right, now, this variant was created just for convenience for the reversal. And the advantage here is that we have one space, Q -1, 1, but fractional indiscernibles. We could easily rework the 48 statements on Q -1, 1 with fractional indiscernibles. We don't bother to do this. The disadvantage is that we don't have a single notion of invariance, as we did with less than 1 Z plus shift invariance. The shift invariance used here depends on the dimension K, because we get somewhat disjointed indiscernibles as we vary the dimension K. So we assume OI max clique less than 1 shift, which I mentioned follows by elementary arguments from each of the 48 statements. And we want to easily derive this variant that we're going to reverse. And it's a very simple argument. Let G be an order invariant graph and let N be given. Let G star be the order invariant graph on. Now we shift up to Q0 N plus 1. You have to use N plus 1 here, to the K corresponding to G. and let S be a less than 1 Z plus shift invariant maximal clique in G star. So we have for all X in Q0 N plus 1 union 1 through N, if X prime is the result of replacing 1 through N in X by 2 through N plus 1, then X is in S if and only if X prime is in S. Okay, that's a consequence of the OI. That's a consequence of this. Now let H be an order-preserving bijection from Q0N onto Q minus 1, 1, sending 1 through N plus 1 to 0 through N over N. We can clearly do that even by nice linear transformation. And that's why we use N plus 1, because you need to know that the count on this set, the count on this list is the same as the count on this list. Since everything we're doing is purely order theoretic, for every X in Q minus 1, 1 union this, if X prime is the result of replacing these fractions by these shifted fractions, then X is an F of S, if and only if X prime is an F of S, where F is acting diagonally. So this is a very simple argument. And then the actual official statement is obtained by setting N equals K. So the reversal begins with this. Every order invariant graph on Q minus 1, 1 to the K has a less than 0, 0 divided by K through K over K shift invariant maximal clique. Now the reversal looks like this. Today, we just finished, actually we're gonna have an introduction. We'll talk about graphs and maximal cliques, and then we'll talk about atomic representation. And that's the end of today. Atomic representation is a very important first major step. We have to show that formulas in a certain language in the related structure are equivalent to atomic formulas. And that's very important because you need atomic formulas or their negation in order to apply the invariance. The invariance is an atomic matter. The next lecture after this is negative reduction and tupling. This is meant to move things into the negative part of Q minus 1, negative part of minus 1, 1, where the action really takes place. The action really takes place between minus 1 and 0 open, right open. So we have to talk about what we mean by the action takes place there. And then we have to develop some tupling. We don't even have anything close to a pairing function yet, and we won't for a while. Even this is weaker than we'd like. Even I think if I remember that this is. Now I'll only do notes here because this is a justification section for all the arguments in 3, 4, 5. What did I do here? Yeah, be careful. Yeah. Okay. Then we pass to a structure Q of 0 infinity because we've already reduced to minus 1, 0 right open. It's more convenient to move the stuff isomorphically to this structure. And then we develop an internal pre-well order in section 10, and then in lecture 10, and then we also form another structure, a second order structure in so to speak in lecture 10. And then we internally develop constructible sets. And then we finish the argument by getting a model of large cardinals from the indiscernibility that's still preserved, Okay. So let's go over some major definitions. A simple graph is a graph G equals VE, where V is the vertex set and E is the adjacency relation. I do graphs in terms of relations. There's an adjacency relation, and E is where the adjacency relation is irreflexive and symmetric. V is called the set of vertices. Yeah, okay, the edge relation, so to speak. We say that G is a graph on V. S is a clique if and only if any two distinct elements are adjacent. So these are simple graphs, so-called. All right. So let G be a graph. It's order invariant if and only if its adjacent relation is an order invariant relation, i.e., for every order equivalent X and Y, X is in E if and only if Y is in E. That's what it means. All right, and S is 0 over N through N over N invariant if and only if for every X here, X is in S if and only if X prime is in S, where X prime results from X by replacing these fractions by these fractions. Yes, as I said earlier. Now we won't be using, that's not what I said earlier. This is much weaker. This is just shift invariance without the parameters, without the interval. And this is really what we want, what we're talking about, this. See, the statement is provable with this. This is what we're talking about, as you'd expect. If and only if for every X in Q minus 1, 0 union, this X is in S if and only if X prime is in S, where X prime results in the shifting. See, and we have the parameters. Here are the parameters right there. Now, these above definitions support fully well-defined invariant max clique minus 1, 1, less than 0 shift, 1 QV. Every order invariant graph on Q minus 1, 1 to the K has a less than 0, 0 over K through K over K shift invariant maximum clique. Okay, in the earlier lectures, we basically proved this, in this other context, which is isomorphic, order isomorphic, for K less than or equal to 2 in Z3, and for K greater than or equal to 3 over ZFC using a K minus 2 subtle cardinal. Okay. All right. So we need some arithmetic here to start. K of 0 is K, K of I plus 1. This is just iterated exponential notation. This is partial functions. The double colon just means partial function. And we start the reversal by fixing a number K, any number K, which is large. And it's not that important. I didn't track exactly how large, but which can be easily done. But I know that 1,000 of 3 is enough. In other words, 2 to the 2 to the 1,000. 2 to the 2 to the 2 to the 1,000. Yeah. Right, the number 3, wow, it's not important. Okay. Yeah, it's it's 3 2s, 222 1,000. It's big enough number. All right, we're going to define a particular order invariant graph on q minus 1, 1 to the k to the 12. So the dimension is going to be k to the 12. And let S be any maximal clique in G, which is also shift invariant. This is also has a shift invariance. Now, the fixed quantity K plays less and less of a role in the proof until finally at some theorem, advanced theorem in the reversal, we entirely remove K from the development, using that K has been arbitrarily chosen up to then, with K at least 1,003. We then derive con SRP with no mention of K. The quantities 1,003 and K to K12 are picked for convenience and safety. All right. We need a further transformation, a further restatement, which is convenient. Namely, let D be the -1, 0 union these fractions. And let J from D into D union singleton 1 be given, which is the identity below 0, and you shift by 1 over K12. All right. And J, of course, is a strictly increasing bijection from D onto D minus well, I didn't mean this. D yeah, just a second. Let me fix this. Yeah, okay. From D onto D minus 0 union. Yeah. Union singleton. Right. Yeah. Yeah, from D onto throw out 0 and put in 1. Yeah. Okay. So every order invariant graph on, so the statement then is trivially equivalent to this, has a J in preserving maximal clique. I want a convenient way to talk about this in terms of a function J, where for all X, X is in S if and only if J of X is in S, where J is acting coordinate-wise. All right, we now define the language L of R, and this is mostly using only certain we're going to only really use only certain finite fragments of L of R, but we will eventually use L of R, but we're going to spend a lot of time with 3 finite fragments of L of R, and we introduced the infinite language L of R first. So L of R is the usual first order predicate calculus with equality based on not, or, and exists, and variables v1, v2, and so forth, and binary relation symbol less than, and the R area relation symbol capital R to the little r. We won't use equality. We don't need to use equality. For semantics, we use the structures q minus 1, 1 less than R to the R. And this interprets the R area relation R to the R under assignments X, infinite assignments X and Q minus 1, 1 to the infinity. Now we optionally use a parameter Q from minus 1, 1 for this semantics. Okay, so XIP is making the ith term P. So this is just the usual Tarskian stuff. where the less than Q doesn't kick in until the quantifiers come in. So this is all completely as expected until we get down to the exist case. And here we have the exist case if and only if there's a P less than Q. Right, so that's the clause where this less than Q really means something. Tells you where the existential quantifiers are to be quantified. Now, here are the three, well, here's how I make up finite languages out of this that are important, the finite languages. See, I'm only going to be able to prove my strong quantifier elimination, meaning atomic representation. Remember, that's what we want. I'm only can make this atomic representation work for certain finite languages only. Eventually, I show that you can derive that it works for the full language, but that requires a lot of work. So we can only do this for finite languages right away. So we have three parameters, N, M, and R. So N, the first one is the complexity. M is the number of variables we're going to use. And R is the arity of the relation. So L of 0 MR is the atomic case, the atomic formulas that we want. And but the atomic formulas where the variable is only among V1 through VM. Remember, I said M here means that there's only M variables in the language. And L of I plus 1 is the same, except that we're going to close under negation, disjunction, and existential quantification. Okay. So N is the logical complexity, M is the number of variables, and R is the arity, as I said. And we use L0 for the fragment without any quantifiers. And the semantics is given the same way we gave the semantics for L of R, except instead of using the elements of Q minus 1, 1, infinity as the assignments, we use the elements of Q minus 1 to the M as the assignments. Now, the main finite languages we're going to be using are L of K1, K1, K, meaning complexity K1, K1 variables. K1 is 2 to the K, if you remember. K1 is just 2 to the K, and arity K for the relation. And K5, K5, K4, and K9, K9, K8. When we use L of K1, when we use this language, we always use the less than Q semantics. We always use the less than Q semantics. The less than Q is not part of the syntax. We were talking about the syntax a moment ago. That has nothing to do with this less than Q. The less than Q is part of the semantics. When we use these other languages, we don't use any quantifiers. So that we don't use the less than Q. There are no quantifiers in here because the subscript 0. No quantifiers. But we still have complexity. So these are quantifier-free formulas of high complexity. That's what we have. But everything's quantifier-free. Okay. And these, of course, reminding you, these use the relationship as RK and RK4 because of here, here, and here, and RK8. All right, now we need some quantities. We need to know, we need a symbol for the number of formulas, in the first language, the number of formulas in the second language, and the number of formulas in the third language. The number of quantifier-free formulas. These are automatically quantifier-free, right? And so we have a technical theorem, which we're just going to display. We're not going to go over. Just some arithmetic, some simple algebra to make sure that we have good estimates on the number of formulas, because we're going to need to enumerate them, work with the enumeration. So we finally get this. This is the point. The number of formulas in the first language we're working with, L of K1, K1, K, is at most K4 over 256. The number in the second language is at most K8, 256. And the third one is at most K12 over 256, just by some algebra. And then we let the phi's be the enumeration of this language without repetition, and these without repetition, these without repetition, these three languages, where the enumeration, they're all without repetition, and we precisely define in the book but never use the details. But we do need one idea. Every formula is listed only after their immediate components are listed, as you might expect. In other words, this is like a build-up process. And it's useful to think of these three numbers as convenient identifiers for the finite languages, which are also the respective arities, right? So those are the three languages. All right, now, you see, this reversal has a lot of twists and turns like this. Why did I set it up this way? Why did I have three languages? Only when we find out much, much later that we have to do something like this. It's not clear from the beginning that we would want to do this. This is the very nature of this reversal. It's actually rather delicate. All right, so the next section is graphs, maximal cliques. All right, a graph is a symmetric irreflexive relation on the vertex set, which is, the vertex set is always this. This is the vertex set. In order to make this reversal understandable, we don't start with the presentation of the all-important order invariant graph G. The reversal depends on defining a complicated graph G, taking an invariant maximal clique there, and then massaging it almost endlessly to get a model of set theory with large cardinals. That's what I'm doing. But if I were to present the order invariant graph, there would be several pages of complicated stuff of which you wouldn't have any idea what the point is. So we don't take that route in the book. Instead, we assume we've already defined G in a certain particular way in terms of what's called declared blockers. And G is completely specified in terms of these declared blockers in the precise manner discussed below. And S is an arbitrarily chosen, suitably invariant maximal clique in G from the statement we're reversing. From the statement we're reversing, we let S be an arbitrarily chosen, suitably invariant maximal clique in this very complicated G. So we have to explain this setup. That itself is somewhat involved, but I'm hoping to make it clear. So we need to know, we have these concepts of how are we going to define a complicated graph for this purpose. So we explain declared sets, declared blockers, and finally the graph G, and how the graph G comes out of this information. And we define it. We finally will define adjacency by X and Y are adjacent if and only if X and Y are distinct, and X does not block Y and Y does not block X. we put a number of stipulations on the declared sets, declared blockers that we adhere to. So you have some idea of what the shape of this is. First stipulation is declared sets are non-empty pairwise disjoint subsets of the vertices, and no element of one declared set is order equivalent to any element of any different declared set. If X is a declared blocker of Y, then Y lies in some declared set. So we're only going to do declared blockers of things that are in a declared set, and X and Y are in, of course, the vertices. If X is a declared blocker of Y, and this is a key idea which cleans things up, if X is a declared blocker of Y and XY and X prime Y are order equivalent, then X prime is a declared blocker of Y. So we have this kind of local order invariance of the declared blockers. It's relative to the thing being blocked. It's relative to the thing being blocked. Second stimulation, if X is the declared blocker of Y, then max X is less or equal to max Y. X is not a declared blocker of itself. X blocks Y. X is a blocker of Y. Y is blocked by X, same thing. If and only if there exists X prime, Y prime, such that X prime is a declared blocker of Y prime, and X, Y, and XY prime are order equivalent. In other words, the blocker relation is the closure of the declared blocker relation under order equivalence. X and Y are adjacent if and only if X and Y are distinct, and X does not block Y and Y does not block X. The blocking relation, X blocks Y, is obviously order equivalent and irreflexive under these stipulations. And the adjacency relation is order invariant, irreflexive and symmetric. So the adjacent relation is going to be a graph. And let X be in some declared set. Y blocks X if and only if Y is a declared blocker of X. If you're in the declared sets, declared is the same as declared blockers are the same as the blockers. All this is evident. Now G is the order invariant graph with the above adjacency relation. Okay. I mean, we haven't, so G just depends on what the adjacent blocking relation is. And that's too complicated to be able to, to be presenting it at this point. There is an official presentation in a special section of the book. This is sort of pinned down later, but it's not in the beginning. So for the additional stimulations, we have four general categories of vertices that are very important. We have the normal vertices, we have the abnormal vertices, we have the exceptional vertices, and we have the stray vertices. The normal ones are where the largest term is the last term, and it's not constant. The abnormals are when the largest term is the next to last term, and the last term is strictly smaller than the largest term. So abnormals are not normals. Exceptionals are when the first term is bigger than all the rest. And those are obviously not normals or abnormals. And strays are none of the above. And it's clear that all these categories are order invariant and partition the vertices into four infinite classes. A normal, abnormal, exceptional set is a non-empty set consisting of normal, abnormal, exceptional tuples respectively. So we have another stipulation. Every declared set is a normal set, an abnormal set, or the set of all exceptionals. See, there's something exceptional about the set of all exceptionals. In particular, no strays are elements of any declared set. Now, I emphasize to you that the manuscript from which this is all derived is going to be put on the downloadable manuscripts page shortly, because I know this is somewhat difficult to take in. All right, the rank of a normal a vertex is the position of the beginning of its longest constant tail. A constant tail is a tail all of whose terms are equal. And the possible ranks of normals range from 2 through K12. The rank of an abnormal is the position of the beginning of the longest constant tail after we drop the last term. And the possible ranks of abnormals range from 1 through K12 minus 1. Exceptionals and strays do not have ranks. Normal rank refers to the rank of normals only, and abnormal rank refers to the ranks of abnormals. Now, here's the main point. If two normals have different ranks, then they're not order equivalent. So this is a numerical way of making sure that two vectors are not order equivalent. And if two abnormals have different ranks, then they're not order equivalent. Of course, no normal is order equivalent to any abnormal. Any element of a normal declared set has a different rank than any element of any different normal declared set. This is a stipulation. And any element of an abnormal declared set has a different rank than any element of any different abnormal declared set. All right. We have the following stipulation, another stipulation. Let X be a declared blocker of Y. X can't be Y. X is not abnormal. Y is normal or abnormal or exceptional. If Y is normal, then max X is less than max Y. And if Y is abnormal, then max X is less than max Y. And if Y is exceptional, then X is exceptional and max X is less than or equal to max Y. The stipulation E holds if we remove declared. Well, it's clear because it was the order equivalent closure. All right, another way of saying it is this. Nothing blocks itself. Abnormals don't block. Strays are not blocked. And all blockers of normals and abnormals have lesser max. Every blocker of an exceptional is an exceptional with no greater max. Okay. Stipulation. The set of all exceptionals is a declared set, and it's a unique declared set that is not normal and not abnormal. The blockers of exceptionals are the exceptional X not equal to Y for which either we lower the max and keep the rest, or we keep the max and the max of the remainder, i.e. the blockers of exceptional Y are precisely those exceptional X not equal to Y, Y not equal to X that are obtained by lowering the first term and leaving the remaining terms the same, or keeping the same first term and the same max. And the point of this comes up when we actually talk about tupling. All right. So we have this theorem that if X blocks Y, then X is not abnormal, Y is not stray, X and Y are not adjacent. Let Y be not exceptional. If X blocks Y, then max X is less than max Y. Let Y be exceptional, X blocks Y if only if X is exceptional and X not equal to Y. And this holds. We drop the first term and keep the second, the remainder, or keep the same first term and the same max. Okay. We have some notation that we need for talking about tuples. So X star M means we stretch X to length M by repeating the last term. And we occasionally use the more complex versions of this. We'll worry about that when we see it. All right. So repeating the proposition we're reversing, every order invariant graph has a J preserving maximal clique. We make the following definition. We now assume that we've actually defined the graph G from the declared blockers, which we haven't explicitly given because it's a complicated list. S is taken to be an arbitrarily chosen J preserving maximal clique in G. And we also need to define this concept. S/N is the set of all n tuples whose stretch is in S. Okay, now the following holds. The vertices outside S are exactly the vertices that are blocked by a vertex in S or block some vertex in S. And if X blocks Y, then max X is less than equal to max Y. The abnormal vertices outside S are exactly the abnormal vertices that are blocked by a vertex in S, because abnormals don't do any blocking. All blockers of abnormals have strictly lower max. All blockers of normals have strictly lower max. There are no blockers of strays. Now, this is very important, this one. Let max X be 1. In other words, I'm using the right endpoint. And X not be not exceptional. Then X is not in S if and only if X is blocked by a vertex in S. If X is not, because you can't do any blocking higher than 1, you see. If X is not in S, all blockers of X have strictly lower max. Any two exceptional elements of S with the same largest and next to largest elements are equal. Any two exceptional elements of S with the same terms after their first term are equal. Now we're going to use the condition max X equals 1 extensively, heavily exploiting condition 3 in this theorem. This is how we really rely heavily on the right endpoint. All right. Now I'm running out of time, so what I'm going to do is get to the conclusion of this atomic representation and talk about it. I don't think it would be easy to explain the all these intermediate developments, but let me get to the punchline of this. Punchline of this. Yeah. All right, here we are. I'm looking at formulas in the first language. Remember, the first language is enumerated, the formulas were enumerated by the letter phi. If I have a formula in this first language, L of K1, K1, K, and remember, they have quantifiers in them. If I have a formula in the first language where the quantifiers are all, where the existential quantifiers only range over less than Q, that it holds if and only if this negated atomic formula holds. And notice that I've used assignments. X is an assignment, and it of course occurs here, but also I have extra constants that have been used. I had to use, sorry, here they are. I had to use an additional set of constants for this representation. And the constant list, it depends on the index of the formula in the list of formulas for the language. You see? And then it's actually the same as this without the negation sign with a +1. Okay. So this is a very strong kind of quantifier elimination. It goes all the way down to atomic. Very important that this comes down to atomic, because it's or atomic or literal, atomic or negated atomic, because this is the only kind of formulas that we can apply the invariance to. It's very important that this is I call this atomic representation for obvious reasons. Now, we've gotten rid of quantifiers in this way and connectives, very important. Quantifiers and connectives this way. For this language. We can only do it for finite language. All right, then we have the other finite language, the other two that are sort of bigger, but they're only quantifier free. So this is a connection elimination result. There's no quantifiers to be eliminated. And we have Y is the parameter. Excuse me, Y is the assignment. V is a set of assignments whose max is less than a half. Something done less than a half or less than or equal to a half. Something done, you can't tell here why I would do that, but it comes up later that it's important that they don't get too high. All right, so and the double max is the double max of something is the regular max if the regular max is greater than or equal to 0, and otherwise it's 0. So this is just a convention to keep things away from the negative. We didn't want to do that. Up here, the negatives were important. Here, they're not so important in the same way. And we're going to have these extra constants. You see? These extra constants are going to be needed to make the satisfaction work. Let's look at what V is, because that's something that I didn't dwell in. It's just trying to remember what. Let's see, where is this V? Here we are. Yeah. Yeah. So it has negative numbers in it, but only up to 0. Yeah, it has negative numbers in it, and then it only has these integers in it. Yeah. Okay, so these constants are always from a nice subset where we are here. Yeah. Okay, so this might be we're talking about max of Y, and Y is in V. Yeah. So this I'm staying away from the negative stuff. So these are again just positive integers. Non-negative integer. Well, positive because I'm adding 1 over K12. Now notice the lengths are very long. You see. All right. You see, this doesn't interfere with theorem 9, because in theorem 9, the Q we start with Q, you see? Q is negative. See, we start with a negative number. Whereas this is the whole point of the max, double max. We don't start with any negative number. Okay. And then we have the same thing for the third language. All right. Now I know this is complicated, and this will be present on the downloadable manuscripts, the whole manuscript for the reversal. But the key takeaway is I have a extremely strong form of quantifier elimination that's actually connective elimination. So we're doing what's called atomic representation. Okay, so Andreas, I think I'm done for today.
Okay, that's fine. And I will now stop the recording.